the first topic which we discuss in this course is transmission lines. Transmission lines is a special case of electromagnetic waves, and essentially it deals with time varying voltages and currents. We saw in the previous lecture that the electromagnetic waves is a subject which deals with time varying electric and magnetic fields. However, as a special case of that, where still the concept of voltage and current is valid, we can discuss the special case what is called transmission lines. The idea in this lecture is to still deal with the quantities like voltage and current, with which we are quite familiar with, but slowly introduce the concept of space in the circuit analysis. As the name suggests, transmission line is a medium which can transfer power from one point to another. So, we can have a variety of structures which can efficiently transfer power from one point to another, and some of them are like a coaxial structure, where you are having the concentric cylinders, there is an inner rod here, there is the outer shell, and you can apply voltage between the inner and the outer conductor, and the energy will propagate along the length of this structure. This structure is called the coaxial cable. We can have a structure where the two conducting wires or rods can run parallel to each other. We can apply voltage between these two rods, and the energy will flow along the rods. We can have a structure where we have a dielectric slab, one side of which we have a conducting surface, and then you are having a conducting strip on the other side. You can apply voltage between these two, the lower surface and the upper strip, and the energy will flow along the strip inside the dielectric. We can have a structure where we have a conducting rod which is placed above a ground surface, and the voltage can be applied between the rod and the ground surface. All these structures can carry power efficiently along the structure. The common feature of all this is essentially we are having a two conductor system across which we apply the voltage, and specifically we deal here with time varying voltage, and as a result of that the current flows and there is a power flow along the structure. So, generically all these structures can be characterized by two conductor systems, and precisely that is what we do when we do the transmission line analysis. That to start with, we do not go into the details of the structure, whether it is a coaxial cable or whether it is a parallel wire transmission line or whether it is a microstrip transmission line or an unbalanced transmission line. We treat transmission line as a two conductor system, at the one end of which we apply a energy source, and at the other end of which we apply a load, and then we do carry out the analysis of power transfer from the source to the load. However, before we go to the analysis of this transmission line, we can ask some very basic questions, and one of the questions is, we are quite familiar with the circuit laws at low frequencies. If the circuit is given to us, we can apply the Kirchhoff's law, we can solve the loop and node equations, we can get the voltages and currents in different branches and at different nodes of a circuit, and the circuit analysis is complete. At low frequencies, when we do the circuit analysis, we take into consideration only the electrical value of the components. For example, if somebody says the value of the resistance is 1 ohms, or if the value of an inductance is 0.1 Henry, if the value of a capacitance is 0.1 microfarad, no other information is needed for the circuit analysis. And the reason is, at low frequencies no other information is needed. If the electrical value of the component is correct, the circuit analysis will be correct and complete. However, as we increase the frequency, the scenario changes significantly. The question one can ask is, if I increase the frequency, would the simple application of Kirchhoff's laws across the circuit element be valid? And the reason for asking this question is very straightforward, that consider a two conductor system which is just a set of two conducting wires. I apply a voltage source at one end of this structure, let us say this voltage is V, and I have connected some impedance at the other end of this structure, and specifically we apply, let us say, a sinusoidal voltage at some frequency f at the input of this structure. So, let us say I have a sinusoidal signal applied at the input of this structure. So, this voltage which I am applying at this end of the line is sinusoidal, which is having a frequency f. Then the time period of this signal will be 1 upon frequency. So, we have time period t, that is 1 upon frequency. So, this time from here to here is one time period. Now, let us say at some instant of time, some voltage was connected across this end of the line. Let us say that voltage is denoted by this point here, which is, let us say, Vp. Now, the fact that no signal can travel with infinite speed in any physical system, this voltage Vp does not occur instantaneously at this end of the line. So, let us say if this end is denoted of the line by A prime and this end is denoted by B prime, the voltage Vp, if applied across A prime at some instant of time, the voltage Vp will not appear at BB prime at the same instant. It will require a finite delay to appear at this location BB prime. This finite delay is what is called the transit time of the signal from this end of the line to the other end of the line. So, let us say if the length of the line is given by L, and let us say this signal or this voltage travels with a speed from this point to this point with velocity v, then we have transit time say Tr, that is equal to L divided by V, where V is the velocity of this signal over this structure. So, this quantity is the velocity. So, now if I apply a time varying signal, then the voltage requires a finite time to travel from one end of the structure to the other end of the structure. However, during this time, this transit time, the voltage at this location is not going to remain at Vp. This signal is continuously varying. So, during this time Tr, the voltage at this location will change to some other value. Let us say that changes to this point Q. So, this point is P, this point is Q. So, the voltage at this location Vq will appear at this location A prime, but at that instant if I see the voltage at BB prime, that will be Vp. So, what we see that when the voltage at this point is Vq, the voltage at this point is Vp. Or in other words, there is a potential difference between the 2 points A and B, and the difference is related to the length. Larger the length, more is going to be the delay or the transit time, and the voltages will be differing significantly at these 2 points. If I take the length which is very small, this point is very close to this, the point P and Q will be very close to each other, and the voltage difference between these two will not be substantial. However, thing to note is, no matter how small a length I take, there will always be a difference in the potential between any 2 points on the line. This effect is what is called the transit time effect, and as we increase the frequency, the role of this effect becomes more and more important. Question then one can ask is, when can I neglect this transit time effect, and when we have to incorporate this transit time effect? The question essentially lies in the discussion which we had. If the potential difference between these 2 points is negligibly small, then we say that transit time effects can be neglected. If the voltage difference between these 2 points is significant, then we say that transit time effects cannot be neglected. So essentially what we say is that if the transit time is much smaller compared to the time period of the signal, then we say that the transit time effects can be neglected. However, when the transit time becomes comparable to the period of the signal, then we have to incorporate the effect of the transit time. Or in other words, what we are now saying is, for carrying out the circuit analysis, the size of the structure or the space has started playing a role, and we can find a condition when the role of the space becomes important. But it is very clear, as we increase the frequency, the time period becomes small. So for the same transit time, the relationship between the transit time and period, this will become much larger or comparable to t. So as the frequency increases, the role of transit time becomes more and more important. When you go to a frequency which is extremely small, that time the time period is very large, and the transit time will be negligible compared to the time period. So essentially, at high frequency, when we carry out the circuit analysis, the transit time has to be taken into account. Without taking transit time, the circuit analysis is inaccurate and incomplete. The condition for including the transit time effect is that when the t is much greater compared to transit time, you can ignore transit time effect. However, when t becomes comparable to the transit time, that time we have to incorporate the transit time effect into the circuit analysis. I can substitute for the t and the transit time from here. So t is 1 upon frequency, transit time is the length of the line divided by the velocity. So the condition is t should be much greater than L divided by V, or 1 upon F should be much greater than L divided by V. I can bring the V this side, so this becomes V velocity divided by frequency should be much greater than the length of the line. But we know from our very basic physics that the velocity divided by frequency is something what is called wavelength. So this quantity is wavelength. So we get lambda wavelength lambda equal to V upon frequency should be much greater compared to the length of the structure. So, if the wavelength of a signal or the voltage which I am applying across the line is much larger compared to the physical size of the line, then the transit time effects can be ignored. However, whenever the wavelength becomes comparable to the physical size of the element, then the transit time effects cannot be ignored. I have to take the transit time effect into consideration. So, as I mentioned, as we increase the frequency, the wavelength becomes smaller and smaller, and the same length, physical length of a wire becomes comparable to the wavelength, and then we have to take the transit time effect into consideration. So, now we have to do the analysis of the transmission line taking into account this effect of transit time. Just to elaborate on this point, what we are now saying is that while carrying out the circuit analysis, the size of the electrical component plays a role. As we saw earlier, at low frequency in the circuit analysis, if the electrical value of the component was right, we get an accurate circuit analysis. However, as we increase the frequency, now the size of the electrical component plays a role. That means, let us say in a circuit I had a resistance of 1 ohms. If I make that resistance in the size of 1 centimeter, I will get some performance. If I make the size of the same resistance over 1 meter, I will get another performance. So, though the electrically the resistance had a value of 1 ohms, since the physical sizes are different for these two resistances, depending upon the frequency of operation, I will get different circuit performances. This is a very important aspect of the circuit analysis. Rather, now we are drastically changing our approach to the circuit analysis, because up till now the circuit analysis was not taking the space into consideration. As soon as we come to a regime where the transit time effects become important, then the space has to be brought into the analysis of the circuit. However, while carrying out this analysis, we still do not want to depart too much from our analytical approach for low frequencies, but still we would like to use the voltage and current laws, but we would like to accommodate the changes which we need because of the transit time. One thing will be immediately clear, that if I take this piece of wire, if I divide this wire into very small sections, then I can always look at a very small section, and that small section will be much smaller in length compared to the wavelength. So, the transit time effects can be negligibly small over the small section of the wire. So, as a whole, transit time effect cannot be ignored, but if I go to the small section of this wire, the transit time effects can be negligibly small. So, I can still apply more or less the circuit analysis, lumped circuit analysis or low frequency circuit analysis. However, if I want that whatever analysis we carry out now is valid at any arbitrarily large frequency, that means at any arbitrarily small value of lambda, then I must take a small section of this wire which is approaching to 0. So, if I take a length of this wire or length of this structure and make it approach to 0, then for any arbitrarily high value of frequency or any arbitrarily small value of lambda, the transit time effects will be negligibly small, and I can still apply the low frequency circuit analysis to that small element. Precisely just the approach essentially we take this structure, divide this structure into small elements, apply the voltage and current laws over the small element, and let that small element size goes to 0, so that whatever relationship we get between voltages and currents that is valid at any arbitrarily high frequency, and that gives you essentially the relationship of voltage and current for a transmission line in the presence of the transit time effects. However, before we do that, we have a small problem, and the problem is, normally when we define the electrical parameter for any component, we define that parameter for the entire component. If I take an inductor, I know the inductor value as a whole. If I take a resistance, I know the resistance value as a whole. However, since I am now going to divide this structure into small segments, knowing the value as a whole does not serve any purpose. I should know the value of the small element, and that is the reason when we carry out this analysis of transmission line at high frequencies, it does not make any sense to define the electrical parameters for the entire length. It will rather be more useful if we define this parameter per unit length of this wire. So, now whatever are the parameters of this, we define these parameters per unit length of this wire. Before we go into this analysis, since we found out a voltage difference between these 2 points, and these are the 2 conductors which are ideal conductors, we may wonder at this point, if this is the ideal conductor, there is no resistance here, then what is making the potential difference to lie between these 2 points? We know if you are the ideal conductor, there is no potential difference across the conductor. However, what we should remember now is that we are talking about the time varying signals, and we are talking about the high frequencies. So, as the frequency increases, the same 2 conductor system, if I see now as a AC electrical element, when the AC current flows in this, you have the magnetic fields around this conductor. So, you have the magnetic fields which are around these conductors, and you have the electric field between the 2 conductors. These magnetic fields linkage with the current, that gives you the inductance of these wires, and the separation between these 2 conductors by dielectric essentially gives you a capacitance between the 2 conductors. So, we have a inductance along the conductors, and we have the capacitances between the conductors. And this inductance or capacitance are not located at any point, but they are distributed all along the length of the structure. These parameters are then called the distributed parameters of the line, and the analysis which we are going to carry out for the transmission line is what is called a distributed circuit analysis. So, these elements are called the distributed elements. So, as I mentioned, the distributed elements are not located at any point, but they are distributed all along the structure, and the better way to then define these parameters are the value of these parameters per unit length of this line. That is what we do when we do the analysis of transmission line, that we define these parameters per unit length. So, coming to the point why there was a potential difference between these 2 points when the resistance of these wires is 0, is that as the frequency increases, the reactance due to these inductance and capacitance increase. So, the reactive elements start playing important role, and that is the reason we have a potential difference. So, although we do not have a resistance for potential difference, there is a reactance now, and its value is going to increase as we increase the frequency. So, from the finite time point of view, there is a potential difference because of there is a finite delay of the signal between these 2 points. From the electrical circuit point of view, I have a potential difference because the reactive elements now start playing more important role. So the dominance of the reactances at high frequencies and the transit time effect, they are the same phenomena, or rather they are the 2 faces of the same coin. So you can look at the phenomena from the transit time point of view, or you can look at the phenomena from the dominance of the reactance point of view. So now at high frequencies, when we carry out the analysis, the inclusion of the reactive component is important. Rather, we will see later that the resistance of these lines is negligibly small, and they are the reactances of the inductance and capacitance. They only play a very important role in transferring power from this end of the line to the other end of the line. So now what we are saying is we define these parameters, the inductance, capacitance, and also we can say in general that these conductors can in general have some resistance. Also the medium which is separating these 2 conductors is not ideal. There are some small leakage current which can flow in that dielectric material, which can be accounted for by introducing what is called a conductance between these 2 conductors. So in general, we can characterize this structure by resistance, inductance, capacitance, conductance, and we can define these quantities per unit length of this line. So what we do now, the distributed element which we now define, they are defined over per unit length of the line. So essentially this structure is equivalent to, you have the inductance, resistance, inductance, resistance, inductance, resistance, like that, and then you have a capacitance, a conductance, a capacitance, a conductance, and so on. So generically any 2 conductor system can be represented something like this, where the inductance which I have represented only in 1 arms is a total inductance which is for both the conductors of the transmission line. So this quantity, if I now measure this quantity, the inductance per unit length of the line, that is the value of the distributed element per unit length, same is true for resistance, capacitance, conductance, and so on. So I now define the quantity R, which is resistance per unit length of the line, L is the inductance per unit length of the line, C is the capacitance per unit length of the line, and G is the conductance per unit length of the line. So the units for R are ohms per meter, L will be Henry per meter, capacitance will be farad per meter, and G will be Mohs or Simon per meter. So now I have defined these quantities which we call as the primary constants of the line, which are the values of the resistance, inductance, capacitance, conductance per unit length of the line. So these parameters are called the primary constants of the line. So for any transmission line, we can define this primary constant. Once we know the primary constant, then the analysis of transmission line can be carried out, as we discussed, divide this transmission line into a small segment, write down the Kirchhoff's law, the voltage and current, and then carry out the analysis in the limit when the size of this segment goes to 0. So, the analysis is valid for any arbitrarily high frequencies or any arbitrarily low wavelength. So, the structure, the transmission line structure which we have, we divide this structure into small elements. Let us take any one of the elements and let us say its length is given by delta x, where x is the distance along the transmission line. Then this small element can be represented by a combination of inductance, resistance, capacitance, conductance with appropriate values, and since I know these values per unit length, I can multiply that by delta x. So, I know this value for this small element. So, this small section of a transmission line is equivalent to a inductance, a resistance, a capacitance, a conductance, and the value of this will be the value of the line per unit length multiplied by the length. So, this is L into delta x, this is R into delta x, this is C into delta x, and this is G into delta x. So, this infinitesimally section of transmission line can be represented by this lumped circuit, and we can carry out the analysis of this small section by applying some voltage V at this end. Now, when you apply voltage V between these two terminals, some current is going to flow in this circuit. Let us say that current is I. When the current flows into this element, which is the series arm of this network, there is going to be a small potential drop across this. So, the voltage at this location will not be same as V. So, let us say that voltage will be V plus delta V. Similarly, the current which I am going to get here will not be same as I, because part of the current is going to be bypassed through this parallel arm. So, the current which you get is this location will be different than the input current. Let us say that is I plus delta I. So, the change in the current from this location to this location is the current which is bypassed through these arms. Change in the voltage is the potential drop across this element. Since the section is very small, this change in the current and voltages are very small. So, if I take the first order approximation to this circuit, the change in the voltage and current can be written on this circuit as delta V will be equal to the impedance of this circuit, which is R delta x plus j omega L delta x. Since the frequency is f, the angular frequency let us say is omega. So, I have here the angular frequency omega, which is 2 pi into the frequency of the signal. So, the reactance of this element will be omega L into delta x. So, I can write the change in voltage, which is minus R delta x plus j omega L delta x into I, and the change in current delta I will be equal to minus G delta x plus j omega c delta x into V. Note here the negative sign indicates that the change in the voltage and current are negative, and that we can see from here. Since the direction of the current flow we have taken is this current will be less than the current at this point. Similarly, there is a potential drop across this element. The voltage at this location will be small compared to this. So, the change in the voltage, the way we have defined that this voltage is V plus delta V and the current is I plus delta I, these quantities are going to be negative. So, that is the reason we have a negative sign here. I can take now delta x common and on the other side, and as we said earlier, if this model whatever we have taken is valid at all frequencies, any arbitrary high frequency, then the size of the element must tend to 0. That means we have to now carry out the analysis of this in the limit when delta x tends to 0. So, if I take that, then I can take limit when delta x tends to 0, delta V by delta x, and we know from our basic calculus that this quantity is nothing but dV by dx. So, that is equal to dV by dx, that is equal to minus R plus j omega L into I. Similarly, from this equation, if I take a limit when delta x tends to 0, delta I by delta x, that will be di by dx, that will be equal to minus g plus j omega c into V. So, what we now see is that the voltage and current, when we take this limit that the size of the element tends to 0, are not related through the algebraic equation, but they are related through differential equations. Here the derivative of the voltage as a function of space is related to the current, and the derivative of current with respect to space is related to the voltage. So, essentially these two are the coupled equations where voltage is related to current and the current is related to voltage. So, the basic relations which govern the voltage and current on this transmission line are in the form of this coupled first order differential equations. So, the major departure from our circuit analysis from the low frequency to high frequency is that at low frequencies we were dealing with algebraic equations. However, when we go to high frequencies, now we have to deal with the differential equations. How to solve these equations? First thing we can do is we can decouple these equations. So, I can take differential of any of these equations once more with respect to space and substitute from the other equation. So, by doing this, I can, let us say I take the derivative of the first equation. So, I will get d2v by dx square, that will be minus r plus j omega L di by dx, and I can substitute for di by dx from the second equation, from this equation. So, I get r plus j omega L g plus j omega c into V. The two negative sign cancel each other, let us say you have positive sign here. This quantity now, whatever it is some kind of a characteristic quantity for the transmission line. because it depends upon the primary constants of transmission line R, L, G and C, and it also depends upon the frequency of operation. Let us denote this quantity by gamma square. So, let us say I define this quantity as gamma square. We will see the physical meaning of what this gamma really means, but at this point this quantity is some characteristic quantity of the transmission line. So, in short, then equation we can write as d2v by dx square is equal to gamma square v. Exactly similar steps if I had taken for the second equation, current equation, that if I had differentiated this with x and substituted from v, I get identical equation for the current also. So, I will get d2I by dx square will be equal to gamma square I. These are now the equations which govern the voltage and current on the transmission line. The quantity gamma is what is called the propagation constant, and we will see in a minute why it is called so. So, this quantity gamma here is propagation constant. Now, the quantity which we have taken here Vi, when we write these voltages and currents, these are the peak quantities or the RMS quantities. If I wanted to have the instantaneous value of these quantities, voltages and current, all of these quantities have a harmonic time variation. That means, though we have not said explicitly, all these voltages and currents have a variation of e to the power j omega t, where omega is the angular frequency and t is the time. So, at any location, if I find out voltage and current that is varying sinusoidally as a function of time with an angular frequency omega. So, if we have to get the instantaneous value of the voltage and current at any location and at any time, essentially this value of the voltage and current has to be multiplied by e to the power j omega t. So, we get the instantaneous value of the voltage at that location. Now, to see now the variation of the voltage and current, essentially we have to take the solution of this equation, and this equation is a very simple second order differential equation with constant coefficient, because gamma is constant for given line and given frequency. The solution of this can be written very easily, and the solution for this equation, let us say you take the first equation, the voltage equation. So, the solution for this can be written as V as a function of x is some arbitrary constant which we have to evaluate, e to the power minus gamma x plus V minus e to the power gamma x. If you have to find the instantaneous value of this, all these quantities have to be multiplied by e to the power j omega t. So, if I am not interested in the instantaneous value, if I want to find out, let us say, the RMS value or the peak value, then I have to can just use this equation. If I have to find out the instantaneous value, then I have to multiply each of this term by e to the power j omega t. So, the voltage now or current on the line is a composite phenomena of space and time, because it depends upon x, it also depends upon the value t. So, the voltage, if I write down as a composite phenomena of space and time, that will be V plus, and let me put this term with each of these terms here. So, this will be e to the power minus gamma x, e to the power j omega t plus V minus e to the power gamma x, e to the power j omega t. The quantity here V plus is a complex quantity and it represents the complex value of the voltage at x equal to 0 location, and the phase of this quantity essentially is the phase in time. So, at location x equal to 0, if I calculate this value, that will be the complex value of the voltage. Now, if I look at the expression now, there are two terms here, and physically these two terms represent different phenomena, and this is what essentially we try to see now. So, let us consider the first term, which is this term. So, let us now concentrate on a term which is V plus e to the power minus gamma x, and let me write down this gamma also explicitly as its real and imaginary part. So, let us say in general the gamma is a complex quantity. So, this has a real part alpha and an imaginary part beta. So, I can write here explicitly now e to the power minus alpha x, e to the power minus j beta x. So, you can write down here total things, this is j omega t minus beta x. So, the first term here has a voltage which amplitude varies exponentially along the line, and the phase of this voltage is a combination of space and time. This is the component which is coming because of space, this is the component which is coming because of time. So, now the first term of this voltage is representing something whose amplitude exponentially varies along the length and the phase of which is a combination of space and time. Let us take a simple case and let us say that I have a structure for which alpha is 0, and we will see little later what that really means, but at this point let us make an assumption that alpha is 0, and let us also, without losing generality, let us say this V plus quantity is a positive real quantity. So, if I assume that V plus is real and positive and alpha is 0, this term, the first term, is for alpha equal to 0 and V plus real. This term is V plus, this is 0, so this is 1 e to the power j omega t minus beta x. I can now ask, what is this term representing physically, which is a combination of space and time now? What is the meaning of this phase? So, if I take the voltage and plot this voltage as a function of space and time, so if I take some value of time and ask what is the voltage variation, so the voltage will be a real part of this quantity. So, if I want to see the voltage, essentially I have to see the voltage which is the real part of V plus e to the power j omega t minus beta x, which is V plus, because V plus is the real quantity, that is what we assume, cosine of omega t minus beta x. So, if I take some value of t and vary x, I will get a function which will be sinusoidal function. If I change the value of t to some positive value, I will get another function which will be shifted now in x. So, if I look at this function essentially in space will look like. So, this is the direction x, and here let us say this is t equal to 0, t1 equal to 0, I have T2 greater than T1, T3 greater than T2, T4 greater than T3, and so on. So, if I take this term and plot for different values of T, take first T equal to T1 equal to 0, then T2, then T3, T4. The function essentially will look something like this. So, if I concentrate on any one point of this function, let us say peak of this function, as the time increases, the point will shift rightwards. It is shifting from here to here to here to here. So, if I look at this phenomena as a total phenomena of space and time, it will appear as if this pattern is moving rightwards. Every point on this function is moving rightward. So, this phenomena is what is called the wave phenomena or travelling wave phenomena. So, the term which we have got here, which has a phase which is a combination of space and time, essentially represents a travelling wave phenomena. And since here we are having a variation of voltage, this term essentially represents a travelling wave in the positive x direction. The wave is travelling from left to right. If I do the same thing for the second term of the solution, which is V minus e to the power gamma L plus j omega t, that will have a phase term for which the sign of beta will be changed. So, it will be omega t plus beta x. That then will represent a phenomena which will be a phenomena travelling in the opposite direction. This is x. Again, this is T1 equal to 0, T2 greater than T1, T3 greater than T2, and so on. In this case, when your function now is the second term of the solution, where the function is cos of omega t plus beta x, the point will appear moving leftward or in the negative x direction. But in both the cases, the phenomena appears to be moving on the transmission line. So, what we see in general, that as soon as we introduce the transit time effects on the transmission line, the voltages, and so will happen to the current, will exist in the form of travelling waves on the transmission line. So, in general, whenever we are having a high frequency circuit analysis, the voltages and currents have to be visualized in the form of the waves. So, we see now from this lecture that a departure from the lumped circuit analysis to the distributed circuit analysis radically changes the approach to the circuit analysis, and now all the voltages and currents, they exist in the form of waves on the electrical circuit.